Welcome back to the deep dive. We're your shortcut, really, to cutting through all that noise and helping you understand complex topics faster. You know how it is, right? New stuff coming out constantly feels like you're always trying to catch up. So that's what we do here. We boil it down for you. Today, we are diving into AI reasoning systems, specifically a new one that's, well, turning some heads. K2-Think, the big deal. It's small, relatively speaking, just 32 billion in parameters. But it's performing like the big guys, sometimes even better than much larger, way more expensive systems.
Okay.
That's pretty significant for AI's future. So the question we're tackling in this deep dive is, how on earth is a smaller model doing that? Okay, let's unpack this.
Yeah, it's fascinating because K2-Think really flips that old script, the bigger is always better narrative in AI. For ages, the whole game in AI reasoning was scale, scale, scale. Hundreds of billions, trillions of parameters, and we saw amazing things from proprietary systems, right? OpenAI's O3, Google's Gemini 2.5, especially in tough areas like math, coding. But that scale comes at a massive cost, computationally huge, and often those top-tier abilities are locked away. K2-Think just walks in not just as a top open source player, especially in complex math, but doing it really efficiently. It really makes you rethink what's possible with smart engineering, not just brute force.
Exactly. And that efficiency, that's the key part for you, the listener. K2-Think isn't just some cool tech demo. Its performance per parameter ratio has real implications. I mean, think about it. This could let a grad student, someone with not much budget or maybe a small startup somewhere without giant data centers. It lets them access and build on truly advanced AI reasoning. It's shifting focus from just raw power to making these tools genuinely open, accessible. It's about democratizing this stuff.
And that's often where innovation sparks, right? When more people get their hands on the tools. K2-Think's strategy, how it punches above its weight, it's not down to one single trick. It's more like a really well-integrated recipe, a mix of advanced post-training methods and some clever test-time computation techniques working together.
Right, no magic bullet, just smart layered engineering. So let's pull back the curtain on that recipe. We need to explore these, six key technical pillars that make K2-Think tick. Let's start at the beginning. How they first taught the base model to sort of think step by step.
Yeah.
That's this long chain of thought, supervised fine-tuning, SFT.
Exactly, SFT, but not just standard SFT. Think of it like putting the base model through a masterclass in structured thinking. It's like showing someone how to solve a complex math problem, detailing every single logical step, not just giving them the final number. So the SFT trains the model to generate these clear, structured reasoning paths showing its work, basically before it gets to the answer.
Okay, and how did they implement that specifically for K2-Think?
They started with the Qwen 2.532B base model, a pretty solid foundation, and they fine-tuned it using this dataset called AM Thinking V1 Distilled. It's essentially a huge library of expertly solved problems, complete with those long step-by-step reasoning traces. Covers math, code, science, various domains. What was really interesting was how fast it improved during this SFT phase. Like, within the first third of the training, they saw these big jumps in performance, particularly on tough math benchmarks like AIM 2024 and AIM 2025. Then performance kind of plateaued, suggesting they built a really solid reasoning foundation quite early on.
Okay, so SFT lays down that strong foundation, teaches it the how, but then how do you make sure those steps are consistently right? How do you refine it for correctness? That's where the next layer comes in, right? Reinforcement learning with verifiable rewards, or RLVR.
Precisely. For K2-Think's RLVR, they brought in the Guru dataset. This thing's a goldmine, nearly 92,000 prompts, where the answers can be objectively verified across 6 areas: math, code, science, logic, simulation, even tabular tasks. The clever part is, instead of relying on fuzzy human feedback, they optimized the model based on whether its outputs were actually correct, like having an automated judge checking every answer.
Okay, makes sense. Optimized for correctness. Did it give a big boost?
Well, here's where it gets a bit counterintuitive, actually. RL did improve performance over the SFT model, but the gains were fairly modest, only about 5% better on AMA 2024.
Only 5%.
Yeah, but then they ran another experiment. They trained RL directly on the original Qwen 2.532B base model, skipping their strong SFT checkpoint. And that approach saw almost a 40% improvement.
Wow, okay, so the strong SFT might have actually limited how much the RL could improve things later.
That's what it suggests. It poses a really interesting question for AI training. How do you best balance that initial supervised learning with later reinforcement? Too much structure up front might constrain refinement. They also found something else interesting. They tried multi-stage RL, reducing the context length halfway through, say, from 32,000 tokens down to 16,000. And that actually hurt performance. It seems disrupting those established reasoning patterns learned earlier is detrimental. Training nuances are critical.
Fascinating. So more initial guidance isn't always better if it boxes in later learning. Tricky balance. But okay, the model's trained now, SFT, then RLVR. But the innovation didn't stop there, right? They use these test-time scaffolding techniques to squeeze out even more performance after training without making the model itself bigger. Let's talk about the first one. Plan before you think. What's that about?
Right. Plan before you think. It's clever. They use a separate, smaller language model, one tuned just for understanding instructions as a kind of planning agent. So when you send a query to K2-Think, this planning agent looks at it first. It pulls out the key concepts and generates a high-level plan, like an outline or a strategy.
But it doesn't solve it.
No, crucially, it doesn't give answers or do the reasoning. It just creates the structure. Then that plan gets tacked onto your original query before it goes into the main K2-Think model. It's basically giving the reasoning model a strategic roadmap up front, like giving that chef an outline before they start cooking.
That makes intuitive sense. Structure helps.
It's very much like human cognition, isn't it? We often do that kind of meta-thinking. We plan, we structure our approach before diving into complex reasoning. This planning phase helps organize the whole process, makes the core reasoning more targeted.
Okay, got it. Plan first.
Yeah.
And then there's the second test time trick, which you mentioned ties into efficiency. Best of n sampling. Bona.
Yep, best of n, or BON. Simple concept, surprisingly effective. K2-Think doesn't just generate one answer, it generates multiple independent responses to the same query. They found Eng3 worked best for them.
3 different answers.
Right. And then another external LLM acts as an evaluator. It looks at the 3 options and picks the best one.
So it generates a few drafts and picks the winner.
Essentially, yes. They did test a more complex setup called Mixture of Agents, which gave slightly better results, but BON hit that sweet spot, good improvement, without adding too much computational cost. It was a smart trade-off.
And these 2 techniques, plan before you think and best of 3, they work together.
They do, and that's important. The gains are additive. Using both together provides a significant boost, somewhere in the range of 4 to 6 percentage points across different benchmarks. So these aren't just tiny tweaks, they're making a real difference to the final performance, getting more out of the same trained model.
And you mentioned a surprising benefit of the plan before you think part, something relevant for the user experience.
Ah, yes. This is pretty neat. Not only does the planning step improve the quality of the answer, but it often makes the final response shorter. They found it could reduce the token count in the final output by almost 12% compared to the model without planning.
So better answers, and more concise too, that's a win-win. Less waffle.
Exactly. More efficient communication.
Okay, so K2-Think is smart. It's efficient in its reasoning, thanks to SFT, RLVR, planning, and a BON. But the elephant in the room for complex AI reasoning is often speed, right? Especially with long chains of thought. How do they tackle the speed issue?
Yeah, speed is absolutely critical for usability. If it takes minutes to get an answer, it breaks the flow. This leads us to the final 2 pillars: speculative decoding and deploying on specialized hardware, specifically the Cerebras Wafer-Scale Engine, the WSE.
Speculative decoding.
It's a technique to speed up generation. Basically, you use a smaller, much faster draft model to predict a sequence of likely next tokens. The main K2-Think model then checks this draft sequence very quickly in parallel. If it's correct, great, you just generated several tokens at once. If not, it corrects it and proceeds normally. It significantly cuts down on that 1 token at a time bottleneck of standard autoregressive models.
Okay, smart prediction. And the hardware, Cerebras WSE.
Right. The WSE is a different beast entirely compared to standard GPUs. Its big advantage is this unique architecture. It manages to keep all the model weights, all 32 billion parameters for K2-Think, directly on the chip in massive amounts of on-chip memory. And it has incredible memory bandwidth, something like 25 petabytes per second.
Whoa, petabytes.
Petabytes. This avoids the constant shuffling of weights between chip memory and external memory that slows down traditional GPUs, especially for these large models where every next token depends on the previous ones.
So what does that translate to in actual speed?
The numbers are pretty wild. They're getting around 2,000 tokens per second out of K2-Think on the WSE.
2,000 tokens a second. Compared to what?
Compared to maybe 200 tokens per second on a top-end NVIDIA H100 or H200 GPU. So roughly a 10x speed up.
Okay, 10x, let's make that concrete.
Okay.
A long response, say 32,000 tokens.
Right. A complex, multi-step reasoning task might generate that much. On the WSE, you're looking at about 16 seconds.
15 seconds. And on the H100?
You'd be waiting closer to 3 minutes.
Okay.
Mm-hmm.
That's not just faster. That's a fundamentally different experience.
It absolutely is. It shifts complex reasoning from something you might run as a batch job overnight to something genuinely interactive. Think about AI agents that need to plan, act, get results, replan, multiple steps. Those delays add up catastrophically on slower hardware. This kind of low latency makes those sophisticated multi-turn agentic workflows actually practical. It makes the AI feel responsive, usable in real time.
It brings it out of the lab and into practical use.
Yeah.
And you mentioned people can try this.
Yep, they've made it very open. K2-Think is available at K2-Think.ai. The code, the model weights are on Hugging Face and GitHub. Plus, there's a production-ready API endpoint you can hit.
Very cool. Okay, the engineering is impressive. The speed is there. Let's talk results. The proof is in the pudding, right? How does this 32 billion parameter model actually stack up against the competition on standard benchmarks, particularly in math, where they seem strong?
The math results are where it really shines, demonstrating that efficiency payoff. K2-Think hits a microaverage score of 67.99% across a suite of challenging math benchmarks, things like AIM 2024, AIM 2025, HMMT 2025, and this very tough one called OmniMath Hard.
67.99%. How does that compare?
Well, it actually surpasses some much larger open source models. For instance, GPT-OSS 120B scores 67.20%. DeepSeek V3.1, which is a massive 671 billion parameters, gets 64.43%.
So it's beating models many times its size.
In these specific math benchmarks, yes, and it's right up there, highly competitive with proprietary giants like O3 High, which scores 68.68%. What's also notable is its performance on OmniMath Hard, 60.73%. These are Olympiad-level problems, extremely difficult. It shows real deep reasoning capability.
Okay, definitely a math whiz. But is it versatile? Or is it just laser focused on math? How does it do elsewhere, like coding or science?
It shows good breadth. It's not a one-trick pony. In coding, for example, it scored 63.97% on Live Codebench. On SciCode, it got 39.2% on the subproblems metric. Both are strong results, often beating comparable or larger models. In science reasoning, it achieved 71.08% on GPQA Diamond. On a benchmark called Humanity's Last Exam, which is notoriously difficult, it scored 9.95%. Not top of the leaderboard there, but still respectable, showing broad knowledge.
So the takeaway is?
The takeaway is that K2-Think really does set a new standard for parameter-efficient open-source reasoning. It's versatile, handles tough analytical tasks effectively, and proves you don't need sheer scale alone.
Right. So for you, the listener, this means powerful reasoning tools are becoming more efficient, more accessible. Frontier performance isn't solely the domain of giant, costly models anymore. Now, with great power comes the safety question. When you build something this capable and make it open, you have to think about safety. Did they address that?
They did. They put K2-Think through a pretty thorough red teaming process using established safety benchmarks, specifically the Safety 4 framework.
And how did it do?
The overall Safety 4 macro score was 0.750, which is, a reasonably solid baseline for a model with these kinds of capabilities. It showed particular strengths in a couple of areas. High-risk content refusal scored 0.83, meaning it's pretty good at saying no when asked directly to generate harmful stuff. And conversational robustness was high, too, at 0.89. It generally maintains safe behavior even over long, multi-turn conversations. That's important for interaction.
Okay, strong refusal, robust in conversation. But red teaming is about finding weaknesses, too. Where did it need improvement?
The evaluation flagged a couple of areas needing more work. Cybersecurity and data protection scored lower at 0.56, and jailbreak resistance was 0.72. It showed some vulnerability, particularly to more indirect attacks, attempts to extract the prompts it was trained on, or requests that could potentially aid cyber attacks.
And the developers are aware?
Yes. Crucially, they acknowledge these findings openly. They state these are active priorities for improvement, and they're working on strengthening defenses. That transparency is exactly what you want, especially with open models.
Definitely. And that openness ties into their whole philosophy here, doesn't it?
Absolutely. Part of the motivation for releasing K2-Think this way, open code, open weights, the API is explicitly about broadening access to this kind of foundation model research. It's also about learning how to effectively battle test, public large language model infrastructure in the real world, and critically ensuring that the lessons they learn during development and deployment, both good and bad, are shared back with the wider research community.
It fosters that ecosystem.
Exactly. It helps ensure the benefits and the understanding of the risks of advanced AI are distributed more widely, developed more transparently and safely.
So wrapping this up, K2-Think's story is pretty remarkable. A 32 billion parameter model performing at the frontier, not through just making it bigger, but through really smart integrated engineering. The SFT, the RLVR, the planning, the sampling, the decoding, the hardware, all working together.
It really is a powerful demonstration of how innovation in training methodology, in test time strategies, and in specialized hardware can completely change the game. K2-Think proves that smaller, highly optimized models can deliver incredible power, making advanced AI potentially much more accessible than we might have thought just a few years ago.
It certainly challenges assumptions. So here's a final thought for you to chew on as we finish this deep dive. As AI races forward, will the future belong solely to these ever larger, often closed-off models needing vast resources? Or has K2-Think perhaps sparked a different path, a move towards more efficient, more openly accessible, more cleverly engineered systems that empower a much broader range of innovators? Something to think about. We definitely encourage you to check out K2Think.ai and see this approach in action for yourself. Thanks for diving deep with us today.